Deep reinforcement learning is one of the most interesting and powerful tools that we have today for developing intelligent systems. I got interested in this because I had been working with simulating multi-agent systems like ant colonies, and I realized that this technique was allowing these machines to do things which really have never been done before. You can get really lifelike behaviors, and part of that is because of the applying these new techniques of deep learning to reinforcement learning. The deep learning part of it allows an agent to take in a more data-rich type of input, like an image or a sound or a three-dimensional environment, and then learn a mapping from that rich input to what action they should take. So I'm going to give just a quick description of this project that I was working on, and to learn everything I needed to know to do this, it took close to 5 months. I started working with this game engine called Unity because they allow you to actually train agents within a simulated three-dimensional environment. I wrote the details of the project up on this new blog, which I'll put a link. I basically want to get this group to transport these objects from one end of the arena to the other as fast as possible. That's the group objective. And we train them on an individual basis by rewarding them for certain types of actions, like going and picking up the ball, which happens automatically if they touch it. They touch the green bin, and then passing it to their neighbor, which is the game kind of takes care of automatically if they touch their neighbor who's empty-handed. And then when they pass it to their neighbor, it turns red, and then they can then move it to the red bin, and they get rewarded for depositing it in that bin, for receiving it from someone who's carrying, for giving it to someone who's empty-handed, and for picking it up. This is using in reinforcement learning what's called dense rewards, as opposed to like sparse rewards, because we're kind of like helping them along at every stage of this process, when the ultimate goal what I want them to do is to just transport these objects as fast as possible from the green into the red, just to maximize that rate of movement. Essentially, in reinforcement learning, a reward is like reinforcing that mapping to that action. So it kind of encourages them to repeat that again the next time they see that scenario. And all the picking up and transferring and the conversion of the ball is done automatically, so it just kind of the game logic, the kind of game automatically takes care of that. So there's no like explicit action for passing it or receiving it or something. They can't like pick it up and then decide to drop it at some point. And so there's a kind of like obligatory cooperation, because they can't actually deposit a green ball into the red bin. What's going on is that there's like a neural network in the head of each of these agents, which is in charge of taking in this input, this sensory input, and then learning a mapping between that and how they should move essentially at that point. So basically, at each point in time, the network that is controlling their movement basically takes in this set of observations, which are what's called these raycast perception, where they can sense the distance to objects in the environment by shooting out these lasers, essentially. How far away is the object that's being intersecting with that laser, and what object was it? So they can basically sense the wall, they can sense each other, they can sense. There's a second tier of raycasts shooting out from above their head, where they allows them to sense what type of object the other agent, the neighbor, is carrying, and they can of course sense the two bins. There's one which is the object that they themselves are carrying, and another thing that they can sense is they have like an internal compass, so they can kind of sense which direction they're facing, like in terms of that's just like an XY vector of like where their forward vector is pointing, and that helps them like learn to. It gives them like a sense of orientation in the space. We can refer you to the paper to look at the details of that, but essentially it's like a really long vector which just kind of concatenates all these different observation types, which is passed to just a multilayer perceptron. So the full vector is something like 35 dimensions or something like that. And then at each point in time, they're able to map that input to an action, which is basically you're going to move forward or not. That's one action branch. And then you can turn by a fixed amount of degrees. So the full action that you can take at one point is a combination of turning right, turning left, not turning, and then moving or not moving. So all of those are possible in one step. I found that it actually scales pretty well to increasing the number of agents. I think this system was trained with 6 agents, and when you add more, they seem to, up to 16 at least, it seems to, they're still able to function and adapt to this environment that they were not trained in. Okay, that is it for this project. Any further details are going to be in the paper that I wrote in the link. And for the time being, I'm taking a pause on deep reinforcement learning to focus more on the computer vision problems, because that's I was able to do this whole project basically just in C# and Unity, and I didn't have to work with TensorFlow and Keras that much. And I'm trying to make sure that I learn that stuff. All the code for the project is in the GitHub repository. With that, I am signing off. Peace.